students, let's start with the new topic today, that is geotechnical engineering. So today I'll be giving you brief about geotechnical engineering and what is it like for a civil engineering student who is preparing for GATE. Frankly speaking, and all of you must be knowing that this subject is the most weighted subject in civil engineering. This is the subject that can turn everything around. This is a subject that can make your mark from 50 to 65. And this is a subject which can fetch you a PSU and not an IIT. That will create difference. From IITian to a person who is taking a job in a PSU, that is Navratna PSU, Maharatna PSU or Mini Ratna PSU, whatever it may be. But this is a subject that will create the difference. And for a civil engineering student, this is the most scoring subject of civil engineering total. So this subject can turn everything around for you. So the net weightage for this subject every year ranges from 14 to 18 marks in GATE. Okay, so net you have 14 to 18 marks from this subject, but it can vary in such a way that, because it's huge, this is a huge number. This is a huge number and its variance is also good. So that means in 2016 there was about 21 marks of question from this topic. 21. Can you imagine that? And I gave that paper and this thing turned around for me. Everything. So this is a very scoring subject, and if you have full confidence and full knowledge about this subject, this will be really good for you. And this is what you have to do. So in 2016 it was 21 marks. So you can look at the variance over here. This is an average of last 12 years which I have put up for you, but this is 2016. So it can repeat itself, history repeats, and this can happen. And this is a very scoring subject, very easy subject, mind you. There are few concepts that students are not able to understand, which are in their doubts throughout the year, and these are not cleared. These are never cleared. And in interview, when you go, what happens is, they ask you from that same thing. Then they will ask you and they will pinch you on that thing, that why didn't you read that thing? Why didn't this concept was in your strength and you had it in you? This is the basic thing what a person wants from you in a PSU when you go for an interview, or an IIT you go for an interview. They'll just put up you on that particular platform and ask you that question, and then you will fail. So that is what this subject is all about. That's what I'm talking about, effective stress. Everyone knows what is effective stress, but they don't know in depth what is actually an effective stress. So everybody knows what is shear strength, but the general aspect about it is not known. What is drained soil? What is undrained soil? What is cohesionless soil actually? What does that phi mean? Nobody knows. That's what we need to know in basic, and from the downstairs you have to study this topic and go at the top level. And that is what we are planning to do. We are giving you, and that is what I'll be teaching you in this whole subject. So this is very, very good subject. It's like the main importance of this subject is its weightage. That is the most pinching thing and the most highlighting thing about this. And then it is the core of civil engineering. So this is the core of civil engineering, and everyone wants to have a great knowledge about this thing. So this will be like so strengthening in an interview for you that will never look before. So let's start with a basic topic which I'll be starting today. I'll be taking up effective stress, and I'll be giving you hints about it, and then I'll be giving you some problems on that later on, and then I'll just try to see you that what you can go with that question. Okay, so this is very important subject. Let's start with it. Soil mechanics. So let's start with effective stress first. What is actually effective stress? Okay, so we'll start with effective stress, and I'll give you a brief about effective stress. So in this topic, effective stress, see, what I will basically tell you that there are two types of soil in intra-bondings. One is physical interaction and other is chemical interaction. Okay, so the physical interaction is basically because of the friction produced between the particles. So when the two particles have friction between them, then what is the most dominant thing? That is the physical interaction. The physical interaction is taking place. What is chemical interaction is? Chemical interaction, there might be some bonding due to molecular forces and all. And these are totally independent on the physical contact between them. So here, what we'll be studying is, we'll be just looking at the point that what is actually chemical interaction. Okay, chemical interaction is, first of all, maybe hydrogen bonding. Then it can be molecular forces like van der Waals forces. It can be like ionic bond, metallic bond, whatever it may be. But the main concern of effective stress is not chemical interaction, it is physical interaction. What is that physical interaction? Physical interaction focuses on frictional strength. That frictional strength can be of two types. Firstly, that can be interlocking between the particles. The frictional strength is actually between two types of things which are basically, that is the interlocking and that is, second is gripped. So when it grips the surface, so this is nothing but gripping. So second is interlocking and second is gripping. So two types of thing you have friction. So friction is nothing but based on two particular things, interlocking and gripping. Now this is my one type of physical interaction. Now my second is cohesion. So the cohesion is also a physical interaction. So physical interaction, what I'm talking about is, there are two different things. One is friction and other is interlocking. So friction, it has interlocking and gripping. Second is we have cohesion. Cohesion in our physical interlocking or physical interaction, whatever you call. Okay. The cohesion are of two types. First cohesion is called as true cohesion. Second is your apparent cohesion. So true cohesion is just van der Waals forces or just the negative positive charge which you would have studied in the type of soil or clay structure. In that one you have dispersed structure and one is flocculated. The flocculated have negative and plus edge and positive charge interaction. So that is nothing but true cohesion is all about between clay particles. They are chemically bound. They are not chemically bonded, they are physically bonded to each other. Other is apparent cohesion. Apparent cohesion is nothing but the capillary, the negative pressure which is created, which sucks in the particle. So that is also cohesion. So these are two types of cohesion which we have, true cohesion and apparent cohesion. So in effective stress topic, we'll be studying basically about these two physical interactions, and that is nothing but causing stresses on the particles. When they interact, there is stress transfer, and that is what we'll be basically studying in this topic. So let's move on and try to study what is actually effective stress. Effective stress is nothing but when you just look upon a thing, and if you look at a soil structure, for example, let's take a soil structure for example. So there might be soil grains up there. Okay. So what happens is, if it is an H height soil, so if we try to study it, there are three types of things which we can see. There are generally three types of things which we can see. What are that? Like, let's study. First, they can be the soil particles. Then there will be a water table also. There can be water table. Absolutely, there can be water table. So effective stress is basically composed of three components. First, we have the total stress. Then we have the pore water pressure. And thirdly, we have the effect. So now, if this is a soil structure which is of height h and water table is at this particular length, and this is my P force also acting on the system, and if I want to consider this point B over here, so if I want to find out the total stress means net loading divided by the whole area. So if its area of cross section is A, so the total stress will be nothing but what? If this is of gamma T, is its soil, total soil strength, it is nothing but the soil unit weight which is given as gamma T. So what will be that? So our total stress will be equal to P plus gamma T into H divided by net gamma T into H into area divided by area. So this is the gamma T, kilonewton per meter cube into area into height will give me nothing but the total stress on the system. So this will be my net total stress. This can be written as P by A plus gamma T into H. So this is my total stress which is acting on the system. Now here we know that when the soil mass is totally into water, the gamma T value changes to gamma saturated. So we say that net gamma T becomes equal to gamma saturated if the water is fully saturated. System is called as gamma saturated. So gamma T is nothing but equal to gamma saturated. So my P by A value will be gamma saturated into H. Now, what is pore water pressure? That I want to know. What is that pore water pressure? So I'll tell you that pore water pressure U, that is called as the next thing, that is the pore water pressure. It is not anything from the sciences. It is not anything which is coming new. It is just what is present. Have you heard any new stress? Okay, now I was till 11th, 12th class, I had never heard of this. Now automatically you are saying there is something called pore water pressure. What is that? I don't know. How does it come? Because we will be studying water and solids, water and soils, water and air, everything we have been studying throughout our lives. But what is this pore water pressure? How does it come? Then everybody thinks about it. Like, what is this? Is this anything new? No, it is not anything new. Pore water pressure is nothing but the buoyant force. The buoyant force which you have been hearing of, it's nothing but pore water pressure. It's just a new term which is like creating some disturbances in some minds of some people. But that is not the case. Pore water pressure is nothing but our buoyant force. Buoyant force divided by area, that is buoyant stress, you can say. Let's call that buoyant stress. And that is nothing but pore water pressure. So how do we measure it? Like if the solid is present, if a solid is present, it will be applying mg downwards. Okay, that mg will be nothing but equal to gamma saturated into volume. Gamma saturated is nothing but what? Kilonewton per meter cube. And that will be nothing but multiplied by what? Into volume. So gamma saturated is kilonewton per meter cube. So m into g. Newton is force, mg, that is the force that is coming downwards. Similarly, gamma wv will be applied. So gamma wv will be applied to it in upwards direction. And what is that gamma w into v? If you divide by the area, that is gamma w into h. And gamma w into h is what? My pore water pressure. That is nothing but equal to gamma w into h. Because if a soil mass is here in water, this, for example, this whole mass is concentrated over here. So gamma saturated into volume will be acting downwards, and same amount of force will be applied downwards, that is gamma w into v. So it will displace that particular thing. And what is this? If I divide by area, this will be giving you gamma w into h, and that is my buoyant stress, and that is nothing but my pore water pressure. Pore water pressure is just measured by a simple thing, like if you just insert a piezometer over here, so the piezometer will be giving you a rise of h units. So this rise of water is h units. That rises up to the water level. So what happens is, this is nothing but my pore water pressure. Now, what is actually effective stress then? Then effective stress is nothing but total stress minus pore water pressure. And that is nothing but sigma bar is equals to sigma minus U, that is nothing but gamma saturated into H plus P by A, minus gamma W into H, that is nothing but P by A plus gamma submerged into H, is nothing but my effective stress. Now what happens, this gamma saturated is minus gamma W is nothing but gamma submerged, it comes from here. Now what happens is the effective stress has increased, but does it happen very apparently? Whenever you apply the load, effective stress generates? No. See, I'll tell you what happens and what the consolidation, I'll connect the consolidation from here. See what happens. What happens is, whenever a direct loading is added, what happens is the water takes all the loading, says increases its water pressure. From gamma WH, it rises to that P by A. So what happens if just when you this if the P is not acting over here, what happens, this is the system. Now the total stress is gamma T into H, this much, this P by A is not present. And your effective stress is gamma submerged into H. Now what happens? As soon as you apply the loading P, what happens? The total stress changes to P by A, and that is totally taken by what? The pore water pressures. So what happens? The pore water takes place, effective stress is constant, and from time to time it transfers that loading from the top to the soil particles, and that's what happens. The water is transferred, the load what is water is taking, that is transferred to the soil particles, and what happens? They increase their stresses and the soil particles come in contact with each other and consolidation happens. The net effective stress, which is the contact force between the particles, increases, and then there is increment in effective stress. Now water completely seeps out of the system. Extra pore water pressure, that is positive pore water pressure that was created, that is expelled out of the system, and now that is intraflocculated and the contact forces between the soil particles is generated, and that is nothing but the effective stress. So this is called the effective stress. Now if you release the stress, automatically there is suction developed, that is called negative pore water pressure, and that will also seep in from time to time. So this was the basic about effective stress, and that I related with consolidation, and that is what the effective stress increases, the shear strength also increases, because sigma bar plus 2C tan phi plus sigma bar is nothing but your effective stress. I'll write that equation for that. Now sigma bar, and then you will be finding out the shear strength also. I'll be relating the shear strength, and I'll be giving you tricks how to solve the quick problems in effective stress. Okay, let's take a problem. I'm taking a general problem, and in that I have included my water table at a distance of 5 meters from the ground level. This is my ground level, and water table is at 5 meters below this particular point. Now, I want to calculate the sigma bar, that is the effective stress, that is nothing but total stress minus pore water pressure. So what is total stress? Total stress is now, see here, net force on the point B. Now I am actually calculating at point B only. So everything is calculated at point B. Now, at this point, what will be the total stress? This soil mass will be completing a stress on this. This will be also hitting it with some stress. So this soil layer will apply gamma T into 5. This soil layer will apply gamma saturated into 3. I'm just talking about the total stress which is acting on that particular point, and that is not including of the other forces. I'm only including soil forces. Please make sure that I'm only including soil forces. So now soil forces is included, and now what is happening? This is gamma T into 5 plus gamma saturated minus gamma W into 3. So the net force acting downwards will be nothing but gamma 5 into 3, and now water table, you know very well that pore water pressure is gamma W into 3. So if you just insert the piezometer, it will rise 3 units in this piezometer. So your pore water pressure will be gamma W into 3, and not sigma bar will be gamma T into 5 plus gamma saturated minus gamma W into 3. So this is sigma bar gamma T into gamma 3. This is my net effective stress. What I'm trying to say is, like, if you want to directly write the effective stress, how will you write? See, whatever this system is there, if water is not present, it will be simply gamma T into 5, or when the water is present, just write gamma submerged into 3. That's it. It's a very simple thing if you can assume. I want to tell you a very important thing over here is, like, if my water table rises here on the ground level, so my net effective stress will be simply gamma submerged into 8. Why? Why will be that happening? Because net water is this much. Here this whole thing will be saturated now, and now this will be also submerged, this will be also submerged. So net will be gamma submerged into H. If I want to show you step by step, what do you write? You will write sigma is equals to, first this will be gamma, this will be changed to gamma saturated. This will be changed to gamma saturated. So you will write gamma saturated into 3 into 5 plus gamma saturated into 3, that is nothing but equal to gamma saturated into 8. And you will write what? Pore water pressure as gamma W into 8. And because that will rise now up till this point. So now if you want to calculate the effective stress, what you will write? You write gamma saturated minus that will be nothing but gamma submerged into 8. Okay, so this is my effective stress. Now what happens? Now what happens if the water table further rises? This is the most important thing. What happens? The water rises to another level, for example, like here. So let's call that as, like, that be 2 meters, and now water table is here. Okay, this is my water table now. This is the ground level. Now what will happen? I'll say that again the effective stress will not change. I have to say that. Why? Let's see. I'll say that effective stress will be gamma submerged into 8 only. So I am saying that further rise in the water table is not changing my effective stress. How is that happening? Let's see. If I calculate sigma, what will be that? See, firstly this will be, water will be applying the net stress downwards, weight. That is the net weight stress. From the upward stress I am subtracting the water inside pressure. So water will be applying definitely some pressure, and that will be nothing but gamma W into, this will be included in the total stress, plus gamma saturated into 5 plus gamma saturated into 8, directly you can say. Now what will be my U, pore water pressure? It will be gamma W into 8 plus 2, that is 10. So now what will happen is my effective stress will be nothing but, this will be what? 2 gamma W will cancel, so it will be what? Gamma saturated into 8 minus gamma W into 8. This will be nothing but gamma submerged into 8 only. So further rise from the ground level of the water table will not affect the effective stress. See, what is total stress is net loading of soil due to weight and any other particle due to weight which is transferring on the system is nothing but total stress. Before I was just telling you the soil weight. Why? Because there was no water table above that. But now this water table is acting as a surcharge. It is like a P by A. So that you have to include in the total stress. Isn't it? Now, if I include that in the total stress, what will happen? Now, the total stress will be included. Now, my pore water pressure, if I just add here, will also rise to this level. So now my pore water pressure, that is nothing but what pore water pressure? That is hitting the soil voids. The soil salt have created a voids, and that the pressure is coming from that particular voids. And those voids are actually giving it upward force from downwards, that is buoyant force, and then that has to be subtracted. This is surcharge weight, but now these net water table will also create a buoyant force, because that depends on the point of volume the water is in it. Okay, so this is how you calculate the net effective stress. Okay, now let's discuss some shear strength. What is shear strength actually? See, shear strength is actually the internal strength. What I will tell you today is, see, the soil particle is such that it cannot fail in compression anywhere, anytime. It will not fail in any type of compressive failure. If you giving it compression, it will never fail. It will never fail, but it will only fail due to shear. Shear forces are internal forces that are developed, and that shear force will try to shear the whole soil mass, and the soil mass will try to combine to each other. They are trying to be combined to each other, but that will not happen because of shear force generation. And that shear force will just disappear because of the loadings which are acting. So the loadings create shear forces, and those shear forces cause the shear failure if the shear strength is less. Now we have been given a shear strength equation like that. So shear strength tau is nothing but C plus sigma bar tan phi. So here is my sigma bar, that is effective stress. C is the cohesion. So strength is nothing but made of two things. One is cohesion and other is the effective stress between the particles. Cohesion, I told you, and this is frictional term. So this is cohesion. I told you we had physical interaction two types. That physical interaction causes one type of strength, that is shear strength, and that is composed of one, that is friction. Tan phi is nothing but mu. Mu that you study in frictional in physics, that mu, frictional coefficient, that is nothing but tan phi. Okay. This is nothing but C, that is called as the cohesion. The cohesion between the particles, and sigma bar is just affected by friction. So that is why sigma bar effective stress is frictional coefficient, is the frictional force. So these two are stresses which combine together and give me shear strength tau. Okay, this tau is my shear strength. Now what I do is, if this is my soil particle and if I apply sigma 3 over here and sigma 1 over here, what is sigma 3? Sigma 3 is principal stress. What is principal stress? I have to tell you, principal stress is a stress which is acting on that plane where no shear stress is acting. So on this plane, so this is nothing but a 3D diagram which I have converted to a 2D diagram. Actually sigma 3 is acting like this and sigma 1 is acting like this, and there is no force in this direction. That is called as plane stress condition, which you have studied in your solid mechanics or strength of materials. So here sigma 3 is acting and here you have sigma 1 acting. There is no stress acting in this particular direction. So these two stresses are acting. So this is considered as a 2D system or a plane stress condition. Here there is no shear stress acting, that is equals to 0. Here on this surface also there is no stress, that is also 0. So net shear stress is 0. So that's why this system is called as the principal stresses. These are minimum or maximum throughout the system. So if a system has principal stresses, it would be the maximum or minimum stress in all planes. The soil particle is made of different infinite planes, and of that particular plane, these two hold as the maximum and the minimum values. Sigma 3 is the minimum, sigma 1 being the maximum, and all in compression, because the soil particles is just in compression, but it won't fail in compression, it will only fail in the shear failure. Now, how to plot this on the Mohr circle? Mohr circle will be plotted if I keep here. See, sigma 3 will be lying somewhat here and sigma 1 will is higher value, so it will be lying somewhat here. But at this point there is no shear stress acting. I am plotting shear stress now. This equation came because this was C, and this is my tan phi. This is my phi angle, which is called as the frictional angle. Okay, you can just call it the frictional angle phi. So this is how we plot the C plus sigma. Y is equals to, this can be considered as C, and this is my X and this is my M. This is my slope tan phi, and this is my intercept Y, C, and this is my equation. But here I have plotted tau as shear strength. Now I will plot these two things. There are two different graphs, mind you. I will plot these these things in comparison to shear stress. Here it was shear strength which I plotted with respect to sigma bar. Now I will plot the effective stress with the shear stress that is taking place. Now here on this surface, this is no shear stress. So this point will be nothing but sigma 3, 0. And we have one more point, that is sigma 1, 0. So now, what is supposed to be is, like I will be teaching you Mohr circle. In Mohr circle, what is it supposed to be? That these two things are nothing but the two stresses which are maximum and minimum, and they cause failure at some point if increased. So I'll just join, and they are supposed to be a diameter of a circle. Okay, let's draw it. So this is my sigma 3, 0, this is my sigma 1, 0. Now this is a diametric circle which I have drawn. Now what is supposed to be is like, each and every point on this circle refers to a plane on this particular system. This is one plane, this is one plane, this is one plane, these are four planes joined together, 1, 2, 3, 4. So there will be some number of planes from passing through it, like this, like this, like this. There will be many planes, isn't it? There will be many planes that can be angled, because this 3D system can be considered of as many planes like this. So this can be cut as slices of bread, you can say, or slices of cake can be cut, and that cut will be showing each and every plane. So that plane is having some stress, and this, so these points, this is also a point, this is also a point, this is a point which is showing this plane, or this one, and this is a point which is showing this plane. Now there will be some different amount of points in the system. Here, this might be showing this plane, or this might be showing this plane, this particular point. Absolutely it can. So this will be showing that plane. So what is that? Actually this point showing is the net x and y coordinate of this point will be giving me nothing but the sigma bar at this point, at this n you can say, and this will be nothing but my tau at n. This is nothing but shear stress. This is my effective stress at that particular point. So this coordinate is sigma bar n comma tau n. Now this is showing one plane, and this is showing other plane, this is showing other plane. So every plane is having tau except these two things. That is why these are called as the principal stresses. Now I will increase my stress. So this curve will shift, this will go there, and if there is a difference is there more, so there can be a bigger diameter circle also be created. There can be a bigger diametric circle that can be created. If the difference is more. If the difference is constant, there will be same diametric circle. Now this will be my sigma 3, 0, this will be my sigma 1, next sigma 1, 0. Now, this is my strength line. All these points, all these planes are below this strength. That means they are safe now. Isn't it? They are safe. But if I increase to that level and the difference is created in such a way that touches this point, this principal stresses at which this touches this point, this type of coordinate is called sigma f bar minus tau f bar. That is denoting a plane on which sigma f bar and tau f bar is acting. These are the failure stresses. Failure principal stress is this two and this is the actual stress of this point. Here sigma f bar is acting and sigma tau f bar is acting. I will call this point as sigma 3 f bar comma 0 and this point as sigma 1 f bar comma 0, because at these principal stresses there are some planes which are having principal stresses now, which have created a failure stress at a different plane which can be inclined to any other plane. So this plane can be this plane also. Here initially this was happening, now it is this thing which is happening over here. And that particular plane is nothing but this plane. So this can be the top failure plane now. So this is all we have in the Mohr circle. One more things which we can relate is, like, see, this is, if this is the center, so what these lines denote is the perpendicular to the principal planes. If this is my plane, this is my minor principal plane, this is my major principal plane. So these are lines perpendicular to it, okay? These are lines perpendicular, so these can be denoted as the lines perpendicular to these planes. This line is perpendicular to it, so this is plane. And these two lines have an angle of 180 degree, but actually the principal planes and their normals have an angle of 90 degree. This is the angle between their normals and this is the angle between them. Both are obviously same. Angle between two planes is the angle between their perpendiculars. These are 90 degree. So here it is 180 degree. So what we can say is that every plane makes an angle with another plane of x degrees here, that will make an angle of 2x degrees over here. So if this is my normal to the minor principal plane, this is my normal to the major principal plane, and this is my normal to the failure plane, for example. This is normal. So angle between them, this is the angle between the major principal plane and the failure plane. This is the angle between the major principal plane and the failure plane. Why? Because this is normal to the failure plane and this is normal to the major principal plane. So angle between them is nothing but what? This thing So this angle will be same as this angle. No, angle between major principal plane and failure plane is same as the angle between their normals. So this is, for example, phi, and this is normal to my major principal plane, because I told you from center, moving away in the direction of major principal plane is nothing but the normal to the major principal plane. And here, if I join this point to this thing, this point, so this is nothing but the normal to the failure plane. So the angle between them here, if it is phi, so here it will be 2 phi. If here it is phi, it will be phi by 2. So the angle between them is phi. And if here is the angle, that is phi. So this is how, if this is phi, sorry, phi I have already taken this one, so let's call it psi or gamma. So this will be what? Gamma by 2. So this is how we calculate the net failure planes and the different amount of planes which are actually cutting. Okay, so you can also derive some few more things, that this is a center of the circle, this is tangent to that, that will be hitting it at 90 degrees. So all that things can be calculated. So you will get gamma is equals to 45 plus phi by 2. Gamma by 2 there you will get. And you will get phi is equals to phi, gamma is equals to 90 degree plus phi. This you can get from here in this trap. So this is all we have in soil mechanics, and this was the basics which I created for this subject. Hope you liked it. I will be